Okay, so today we are going to be talking about chapter 4.5, which is the Fundamental Theorem of Algebra. Get the PowerPoint going. All right, so the Fundamental Theorem of Algebra. This states that a polynomial f of x with a degree n, when n is greater than or equal to 1, has at least one complex zero. Basically, any polynomial function with a degree of 1 or more has one or more solutions, complex or otherwise. A graph can either have real or complex zeros, as we saw in quadratic equations. So when we're talking about complex zeros here, by the way, we're just talking about anything with an I in it. So like 2i would be a complex number. Maximum number of zeros. Well, polynomials have a minimum number of zeros, which is always going to be 1, assuming that the polynomial actually has an x value somewhere in it. They also have a maximum. The maximum number of zeros a function has is equal to its degree. So a quadratic equation can have 2 zeros, which you've seen plenty of times before. A cubic function can have 3, a quartic function can have 4, so on and so forth. A quadratic equation, that's what I just said. Quintic equation can have 5. So if you're told that all the zeros in a polynomial are distinct, that means that the number of zeros it has is equal to its degree. So for all of these cases, if we assume that all of the zeros are distinct, which they are actually, but doesn't really matter, we know that this one is going to have 3 zeros. So we can identify one of them as real, because it hits the x-axis here. The other two must be complex. There's no other way to do them this way. Since we see the entirety of the line, presumably it keeps going on forever in this direction and then in this direction. It only crosses the x-axis once. But if we know that it has 3 distinct zeros, then 2 of them are complex. This one has an x squared, which means there are 2 possible zeros. Again, since we're saying these are both distinct, those zeros are both going to have to be complex here. Let's write these. 1 real, 2 complex. This one, since it just has 2, there are none that are actually hitting. We know that they are both complex. This function right here is negative x to the 4th. So there are going to be 4 total distinct zeros. We've got 1 here that's real. We've got 2 here that are real, which means we must have 2 that are non-real. So we have 2 real, 2 complex. I'm trying to write super small so that doesn't look very good, but so that part's pretty easy. This is where it gets a little bit trickier. We can actually backwards construct a polynomial from its zeros, the degree, and the leading coefficient. For example, if a function has a degree of 4, a leading coefficient of 2, and zeros of -3, 5, I, and negative I, we can construct a function based on all of this. So first of all, we have a leading coefficient of 2. That's going to be our first part. Then we've got a 0 at x equals -3, which means we have a factor of x plus 3. We have a real 0 at x equals 5, which means we have a factor of x minus 5. Then we've got 1 at I, so we're going to have x minus I, and then we're going to have x plus I. Now, doing this simplifying this, actually multiplying it all out, is going to take a little bit of time. I would strongly recommend whenever you're doing this, try to get rid of i's as fast as possible, and then move on to the real zeros afterwards. So we're going to start with these two. We have x minus I times x plus I. When we multiply this out, we'll get x squared minus xi plus xi minus I squared. Now, minus xi plus xi, these cancel. So we're left with x squared minus I squared. We know that I squared is equal to -1. So we have x squared minus -1, which is x squared plus 1. So now we're going to bring in this x minus 5 term. So we've got x squared plus 1 times x minus 5. That's going to give us, we'll take the x squared, multiply it through first. So we'll have x cubed. We'll have minus 5x squared. Then we've got 1 times x, so plus x. And 1 times -5, so minus 5. So this is our new one. Then we take this and we're going to multiply that whole thing by x plus 3 because it's our last factor. So let's do x cubed minus 5x squared plus x minus 5 times x plus 3. Like I said, this is kind of a long, drawn-out process. And personally, when I'm doing these, I like to just multiply one term through at a time. So I'll do the x first in this case. So I'd get x to the 4th, x times x cubed, x times negative 5x squared is minus 5x cubed. X times plus x is plus x squared. X times a minus 5 is minus 5x. And then we'll do the 3 all the way through. So we've got plus 3x cubed. Then we've got minus 15x squared plus 3x minus 15. When we're simplifying these, we can always take the biggest term and the smallest term and just bring those out. So we'll start with an x to the 4th. We'll end with a minus 15. And then we've got minus 5x cubed plus 3x cubed. So we've got minus 2x cubed. We've got a plus x squared and a minus 15x squared. So we're going to have minus 14x squared. And we got a minus 5x and a plus 3x. So we're going to have minus 2x. Sorry, I kind of ran out of room. And this is going to be our final function here. Now you'll notice that this told us that the degree is 4, and we kind of came to that on our own. The reason that we actually want to be given this degree will make sense in a little bit when I talk about multiplicity. But just to double check our answer, we got x to the 4th minus 2x cubed minus 14x squared minus 2x minus 15. That's not what it says here. Oh, because I didn't distribute the 2. And then we have to multiply everything by 2. So 2x to the 4th minus 4x cubed minus 28x squared minus 2x minus 30. Okay, there's all of that there. Sorry, I just completely forgot about this 2 that's right here. But the actual multiplication is correct. If you multiply each of these terms by 2, you'll get that. Okay, moving on. The conjugate zeros theorem. Now, this is going to sound a little bit complicated, but it's actually very, very helpful, and it's really not as difficult as it sounds. So one of the nice things about complex zeros of a function is that the complex zeros come in pairs. If you have a function with all real coefficients, which means that you've got you have 5x cubed plus 3x squared minus 17x plus 2. All of these are real numbers, right? The 5 is a real number, the 3 is a real number, the 17 is negative 17, whatever. What they're talking about when they're saying as long as your coefficients are all real numbers is that you don't have 5ix cubed in your original polynomial, which we won't deal with at all in this chapter at least. So if you have a function with all real coefficients, no I values in your function, and if a plus bi is a complex zero of the function, a minus bi must also be a zero of the function. So basically, this is because we need to cancel out the I values. If you leave I values in your actual equation, you're going to end up with I's in your coefficients, and we don't want that. So using the conjugate zeros theorem is probably best done through an example. So let's determine a cubic polynomial with real coefficients, a leading coefficient of 2, and zeros of 3 and 5i. So first of all, since it's cubic, we know that our final degree is going to be x to the 3rd. We also know that our leading coefficient is 2, so let's write that out first, and this time I'll actually remember to multiply it. And then we've got zeros of 3, so that one's easy. We got x minus 3. And then we've got 5i, so we have x minus 5i. Now, because of the conjugate zeros theorem, I have x minus 5i. I know that x plus 5i must also be a 0. So if you write out my factors and I have x minus 5i, because again, this is positive, so when x is equal to 5i, this is a 0. So we have x minus 5i. If I have this right here, I have to have the other version. If I had 3x squared minus 2i, then I would have to have 3x squared plus 2i as one of my functions. So you're doing the exact same equation, you're just flipping the symbol in between the two. Let me get rid of that really quick. Okay, so then we want to go ahead and multiply this all out. I know, joy, super fun. Again, easiest to start with the imaginary numbers. So we have x minus 5i times x plus 5i. This will give us x squared minus 5ix plus 5ix minus 25i squared. These will cancel. That's the entire point of the conjugate zeros theorem. So we're left with x squared minus 25i squared. This is equal to -1. -1 times -25 is positive. So we're going to have x squared plus 25. Then we've got our x minus 3. So multiply this, x minus 3. So x times x squared is x cubed plus 25x. Then we've got minus 3 times x squared, so minus 3x squared, and minus 3 times 25, that's minus 75. So we've got all of this, and then we need to multiply this whole thing by 2. I'm actually going to remember this time. So this would give us, whoops, let's just put this here. This is equal to 2x cubed plus, or no, we want to put them in the right order. So we'll have the minus 6x squared next, plus 50x, and then plus 150, minus 150. Okay, and this should be, whoops, my final answer. So my final answer is going to be 2x cubed minus 6x squared plus 50x minus 150. 2x cubed plus 6x squared. Or was it minus? Might have been minus. See, I forgot it. Plus 50x minus 150. Is that right? Is it plus minus? I don't remember what the symbols were. Point is, okay, there. That's what it should have been. I had it right the first time. So 2x cubed minus 6x squared plus 50x minus 150. All right. Next up, I can't actually see what it says because my face is in the way. Finding complex zeros. So if we want to find the complex zeros of f of x equals x to the fourth plus x cubed plus 2x squared plus x plus 1, given that one of the zeros is negative I. So since we have one of the zeros is negative I, we have an x plus I as one of our factors, which means we have to have the opposite. We have an x minus I. Multiply these out, x squared minus xi plus xi minus I squared. This is x squared plus 1. So now that I have x squared plus 1, the way we want to do this next is we're going to actually divide polynomials again. So good old-fashioned fun times x cubed plus 2x squared is x plus 1 divided by x squared plus 1. Now, dividing this again, we're going to get an x squared to start. That gives us x to the fourth plus x squared. Subtract these, and we're left with x cubed plus x squared plus x plus 1. So next up, we divide into x cubed. That gives us x. When we multiply that back out, we'll get x cubed. The x, that won't be there, so we'll have plus x. Subtract these terms are gone. We've got x squared plus 1. We divide these out, and we'll get plus 1. X squared plus 1 over x squared plus 1 is 1. So we have x squared plus x plus 1 left. So then we need to factor this and solve it. This one is, again, going to use that same thing. So what we should end up having is, oh boy, is this even factorable? Ugh. Over 2. Okay, so that's square root of 3. So we'd have x plus, oh, hold on. I feel like I might have. Sorry, this is taking longer than it should. So this one, we're going to simplify down. This is going to be our other zeros, or the plus or minus here. So x minus 1 plus square root 3 over 2. This is also over 2. And then we're going to have x plus 1 over 2. No, it's still going to be minus. Except it's the opposite, so it is going to be plus, sorry. Plus, and then minus square root 3 over 2. So these will be their other factors. Yeah, so, oh, it should have been with an I. I knew that. This is -3 in here. So basically, we'd get these as our answers. It's plus or minus I square root 3 over 2. I wrote them all out as factors. But if we solve this down, right, we'll get -1 plus or minus the square root of -3 over 2. That's -1/2 plus the square root of, or plus or minus the square root of -3 over 2. We can bring the negative out as I, so we'll have -1/2 plus or minus I square root 3 over 2. And this is that factor right here. And then we got the I right off the beginning because of the conjugate zeros theorem. Okay, and then let's see. I think this is the last thing we're talking about. So solving a polynomial equation. We want to solve x cubed equals 3x squared minus 7x plus 21, given that 3 is a zero of f of x. So first thing you want to do, of course, is get all of your variables on the same side. X cubed minus 3x squared plus 7x minus 21 equals 0. We know that one of the zeros is 3, so we have a factor of x minus 3. Next thing we want to do is divide these out. That'll give us our quadratic that'll be left, and then we can solve from there. So 3x squared, this I might not have enough room over on this side. 21 divided by x minus 3. Now, I could use synthetic division if I wanted to here, but I'm going to go ahead and just do it the long way because that'll be a little bit easier to show, and I think we need as much practice with that as we can get. So x cubed minus 3x squared. Hey, what do you know? Subtract this out. This goes to 0, 0, which means we have plus 7x minus 21. 7x, this will go in 7 times, so plus 7. And when we multiply this down, we'll get 7x minus 21, which when we subtract is 0. So we have x squared plus 7 left, basically. X squared plus 7 times x minus 3. This is our full quadratic now, and we're going to go ahead and factor this x squared plus 7. So again, we'll probably see, we can just use the quadratic formula. So we'll have 0 plus or minus the square root of 0 minus 4ac, which is 28, all over 2. So we're going to have the square root of a negative number again, which means our solutions are going to have I in them. We can factor out a 4 from this, so it'll be 2 square root 7. And then we can cancel the 2's, right? So this is square root of 28 is equal to 2 square root of 7. For 2, there should be an I here. Cancel the i's, so we have plus or minus the square root of, or I square root 7. So x equals 3 comma square root I square root 7 negative I square root 7. It should be our answers here. Yeah, so 3 and plus or minus I square root 7. So the main thing is, generally speaking, they're going to give you enough zeros that you can divide down to get a quadratic, and once it's a quadratic, you should already know how to solve that. That's it for this lecture. So this stuff, like I said, is building on all the other things. It continues to get more and more complicated. We're going to be using I's a lot more in this section, so this is definitely another good one to get a lot of practice in, and we will talk about this one more in class as well.